Okay, so we're looking at calculus. She's asking about calculus 2016 problems.
I think I know what she's asking.
Okay, on number 8. Okay, she's asking about number 8. Um, for number 8, it's
Oh
asking.
yeah, it confused me too.
You can bring it up. Okay. All right. So for number 8, let me take the screenshot here and put it in the other one, in my paint. Okay. Paint is over here, actually. Okay. Let me make this bigger. Okay. So I guess there was a sneeze that I thought was going to come, but it didn't come. Anyways, so particle moves such that velocity in v meters per second is related to its displacement, obviously, by the equation. So this is the equation for velocity, and that's the particle's acceleration. So we need to find the acceleration in terms of s. So we know that acceleration is dv dt, right? Right?
Yeah.
So we know that since acceleration is dv dt, we know that this is going to be the derivative of this function up here. So you can write d dt of arctan of sine of s, and then and then what's if you were to calculate the derivative of this with respect to, wait, what's going on? Oh, got them. Okay, got them's entered. Okay. Trudy says, okay. Am I doing something wrong here?
Arc dvdt arc tan sine of s. Yeah, I mean that's what. Yeah, that makes sense.
MG, sorry to interrupt. Quick
Mm-hmm.
question. What page in the Oxford Study Guide is the like exam-like questions section?
I don't know. I just searched up exam style. Just hit Control F and then search up exam style. No
Exam
problem.
style? Okay,
Yeah.
all right. Thanks.
Okay. Yeah. No problem. But how do you differentiate with respect to t
See,
of arc?
that's the question. So what she ended up doing is multiplying velocity times dvdt. So it's v times dvdt. So
Okay. Well, here.
it was like what's that called? Implicit differentiation. Or no, not that's not it. But it was her solution was v times dvdt.
Okay. So I think what you would do is you would probably do chain rule, and then you would, here, let's do this. So if we were to differentiate this, we would have 1 over 1 plus sine squared s, right? And then we would multiply that by cos s, because that's the derivative of sine s. And then we would have s prime of t, right? Because we have to differentiate s, because s is a function of t, and we're differentiating with respect to t, right? So we would have to multiply by s as s prime of t. And what is s prime of t? S prime of t is just the velocity. So that's why we can write this as v, because s prime of t is the v cos s over 1 plus sine squared s, right? And then v is just arctan sine s. So we can write this as arctan of sine s times cos s over 1 plus sine squared s. Does that make sense? So because here's the thing, it has to be differentiated with respect to t, and since s depends on t, we have to differentiate it using chain rule. So that's what I would do. I think that's what she was asking as well on when she asked, why do we do v times dv dt? And this is exactly why. So I wouldn't put a equals v times dv dt, because that wouldn't be true. It is dv dt. It's just that the velocity happens to be part of the function. Hopefully that makes sense, Trudy, if you're watching this later. Okay, all right. So now for this part B, let's just finish it up since we're doing this problem. Using an appropriate sketch graph, find the particle s displacement when its acceleration is 0.25. So what are we sketching? A or S? Sorry, I'm not understanding. Or do you guys understand what the question is asking for?
No.
This is 2016, right?
Mm-hmm.
Let's look at the answers. So I'm not understanding what the question is asking for. Using an appropriate sketch graph, find the particle s displacement when its acceleration. So what, are we plotting acceleration versus time? Or are we plotting acceleration versus s? Maybe that's what it's asking. Zachary, do you know? S A maybe, is that what they're asking us to plot?
Not really. I don't really know.
Okay.
I'm confused.
That's okay. Let's look at what the solution says. And this is what question? Number 4?
8.
Or 8.
I think.
Okay. Oh no. Okay. Which number 8?
First one?
Or okay. This is 16, number 8, but it's on TZ. Okay. Is it missing number 8 on here?
No, it has it, because I remember seeing the solution.
Oh wait, is that it? I think this is it. Okay,
Yeah.
so they're plotting A versus T. Okay, well, we solved that. I don't think so. That we figured out. But then why are they plotting A with respect to T? That's what I'm confused about. Also, how do you plot A with respect to T? Because you don't have a function. Is that supposed to be an S?
Yeah, because it says y is equal to a of s. So
I mean, it could be A of S. That's not a problem. I'm just saying maybe that might be S. Let's graph this on decimals real quick and see if it were S and see what it would look like. Because that's I think that question is very weirdly worded. Decimals. Arctan of sine of S, right? Arctan of sine of S times cosine S. Oh, maybe we need to write this as X, because otherwise, pretend X is equal to S, all right? And then this whole thing divided by 1 plus sine squared of X. 1 plus sine squared. Does that notation work on decimals? Yes, it does. Okay. Does that look like what's in the solution? Kind of, right? Yeah.
The second.
I think it does. Yeah, that should be an S here, not a T. So So the question is asking for a sketch of an acceleration versus S graph, essentially. So that should be an S as we've drawn it. And since this is paper 2, you're allowed to use your calculator. And then you would look at this, you would look at the graph, and you would figure out when the acceleration is 0.25, what is the displacement? So you would have to look for 0.25. So rather what we could do is we can say, well, here's what we can say. We know that acceleration, we want acceleration to equal 2.5. So if we do the function of acceleration minus 2.5 equals 0, we can see where it intersects the x-axis, and then we can, or the s-axis, and then we can see where that the displacement is that. You understand what I'm saying? So if we say, wait, that doesn't look right. Something's wrong. Did I do something wrong? Oh, I see. No, should be right. Minus 2.5, right? Oh, I see what happened. It's 0.25. Yeah, there we go. There we go. There we go. Okay, so now you can see wherever it hits 0, the acceleration equals 0.25, which makes sense, right? Or no, do you not understand what I did?
No, yeah.
Okay, okay. So acceleration equals 0.25, so if we subtract that, now it equals 0. The acceleration equals 0 when, so you would have to sketch this. And the way you would sketch it, it's going to be difficult to sketch on here. So I'll try my best, but to me, it looks like it's going up and then down, right? Yeah, it looks like it's going up and then down. So let's just do that. Looks like it's going up at a certain point and then down at a certain point. Okay. So it intersects at 0.296 and 918. 296 and 918. Okay. So this we would say 0.296, and this would be 0. What was it again? 918, right? 0.918. The other thing we would have to specify is that this is a minus 0.25. Otherwise, we could get points taken off because that, yeah. Then because you're doing a sketch, you would also probably want to label the maximum point. I'm not going to do that just because of time right now, but you can see that the particle's S's displacement is when the acceleration is 0.25 is going to be 296 and then 0.918. I believe those are the two solutions.
MG, you used chain rule on the beginning, right?
Yes.
Because of like S is dependent on T.
Yes.
Okay.
Yeah. If you want to make it really clear, what you could do is you can write this as S of T, because technically S is a function of T, so you can write it as S of T. So if that helps you see it better, that you're differentiating with respect to T, so that's why I have to differentiate S prime of, or I have to differentiate S of T to get S prime of T. That might be a better approach as well. And remember,
so like dv ds times ds dt is equal to dv dt.
That's a good way to think about it as well. Exactly. No, that's a great way actually. If you immediately, instead of dv dt, you think of it as dv ds, and immediately apply the chain rule times ds dt. Yeah. That's probably an even better way to think about it. You're right. And then realizing ds dt is in fact the velocity. So this is v dv ds. So notice that this is dv ds, not dv dt though, right?
Mm-hmm.
Yeah, this is probably the better conceptual way. What I did works, it's not as elegant, so I would actually recommend doing this. Okay, good. Okay, hopefully that clears up that question. All right, cool. Okay, I think we're good with that one. So actually I'll need this to do the questions. But now let's move on to some of the IB questions from here. Let's do maybe one or two of these. Let's do one or two of these questions. Maybe let's do. This looks like it's an interesting question, right? Yeah, let's do this question right here. Number 32, paper 1. And let's scroll down to the solutions so we make sure to have that. Number 32, paper 1. Give me just a moment. I can find it on here. Chapter review. You guys see it? Exam questions. We're on number 32, right?
Yeah.
Okay. All right, good. So let me take a screenshot of this and then put it into Paint. And then let's also make sure to put the questions. Okay, that didn't work. Okay. Okay, all right. So let's go ahead and try this. So it says a crude oil well W lies 75 kilometers offshore. Okay, so this oil well, so this is 75 kilometers offshore. Okay, an oil company is planning to construct a pipeline in 2 linear sections. The first section will run underground and take the oil from the well to a point A on the shore. So this line right here is the shore. Okay, so we have a point W to A. And then the second section will run above the ground and will take oil from A to a harbor H. Okay, so this is from here to here. So now all distances are shown in kilometers. Find an expression in terms of x for the total length of the pipeline. Okay, who wants to try that one? For the total length of the pipeline. How would you figure that out? This actually doesn't require any calculus. This one I think we can do without calculus, right? Because you want to try it, Maham, or do you want to?
About 70. I wasn't even. I kind of zoned out for a second. Okay.
Oh, it's all good. So if we're finding, so this is, the pipeline is running from here to here and then from here to here. So how can we represent the total length of the pipeline? So the first is, this is a right triangle. We can do square root of 75 squared plus x squared, right?
Yeah.
And then we can add, we just have to add, because this is linear, plus 100
Minus x.
minus x. And then 75 squared, you would probably want to simplify that, but this is paper 1, right?
Mm-hmm.
Since it's paper 1, you probably wouldn't have to simplify that. Okay, let's try B and C, and then we'll check our answer, okay? So number B. It costs, or part B. It costs the company
three. Expression. I didn't read that. I thought that's
okay.
And I was like, that's why. Okay, yeah. Sorry.
Costs the company 3 times as much to construct a pipeline below ground. So this portion is below the ground. So this is 3 times as much, and then this is just normal. Okay, this is normal cost. Determine the value of x that results in minimum construction cost. So Maham, you were actually asking about optimization. So this is an optimization problem. So let's go ahead and do it. So value of x that results in minimum construction costs. Okay. So what would be the total cost? If we had to represent the total cost, what would it be?
It costs only 3 times as much to construct a pipeline below ground than it does above ground. Are both?
So this is below ground. WA is below ground and AH is above ground.
Okay, so you would do
the cost as a function is 3 times
the above ground, or the.
Well, it's above. It's 3 times the cost of the above ground, but the way you would have to think of it is it's 3 times the square root of 75 squared plus x squared, right? Mm-hmm. Because that is the that's saying that whatever length this is, I'm going to multiply 3 to get the cost of that, and then obviously 100 minus x is just 100 minus x, right? Mm-hmm. So now what we actually have to do is now we have to find the value of x that results in minimum construction costs. So when can we find minimum cost? Well, we just have to find dc dt, right? Or not dc dt, dc dx, right? Because if we can find the derivative of c and then see where it equals 0, that's going to be an extremum, right? So if we can figure out whether that's a minimum or maximum, then we can figure out whether, that's the cost, right? So dc dx is going to be what? Well, we can, let me rewrite c real quick. I'm probably actually going to put the 3 inside the radical just to make our lives a little bit easier. I don't know if that will make our lives easier, but we can try. This is going to be 3. If I put that inside, that'll be 9 times 75 squared plus 9x squared, correct? So that's the radical portion. plus 100 minus x. Okay. So the derivative of the radical portion is going to be 1/2 times the square root of whatever's inside to the negative half, or whatever's inside to the negative half. So this will be square root in the denominator. And then you'll have the 9 times 75 squared. And then you'll have plus 9x squared in the bottom right here. Then you'll have the derivative of the inside function. The derivative of the inside function is just 18x. So you can put 18x on the top here. And then obviously we have plus 100, which is a constant, then minus x, whose derivative is just minus 1, right? So we don't need to worry about that. Okay. Now what you're going to do is now we want to set this equal to 0, right? Because we want it to be an extreme point. So we set this equal to 0, and we say, okay, well, now we just have to solve for x. So 18x over, so if you actually pull the 3 back out now, this will be 2 times 3 is 6, root 75 squared plus x squared equals 1. I just moved the 1 over. So now you can simplify this a little bit, cancel that, make that a 3. So now we know that 3x equals square root of 5 squared plus x squared. Square both sides, we get 9x squared equals 75 squared. Oh, sorry, 75 squared plus x squared. Subtract x squared from both sides, you get 8x squared equals 75 squared. Then you get x squared equals 75 squared over 8. And then obviously x is going to equal 75. Technically, we should be taking the plus and minus square roots, right? But obviously, it doesn't make sense to have a negative in this context. So we need to make sure we just take the positive square root. So this would be 75 over square root of 8. And square root of 8 happens to be 2 root 2. And if we wanted to make this look nice, we can radicalize it, put a root 2 there, and then make that a 4. Okay, so at this x value is when we would have minimum cost. Does that make sense, Mahan? This actually isn't an optimization problem. This is just a relative, but this is basically the foundation of optimization. If you can understand minimum and maximum, optimization is literally just that, and then you just substitute.
Okay.
And then part C, hence, show that the total length of the pipeline is 75 over 2 root 2 plus 100. So we found x, so now all we have to do is just plug that back into the total length. So we know that the total length is square root of 75 squared plus x squared plus 100 minus x. So now we just put the x, substitute x in. So now we have 75 squared, and this was originally, well, x squared happens to be 75 squared over 8. So we can put a 75 squared over 8 here. And then plus 100 minus 75 root 2 on 4. Okay, so now we just have to simplify this. I'm running out of space, so I'm going to actually start working on this side. Okay, so this is going to here. Okay, so 75 squared plus 75 squared over 8, I can factor out a 75 squared, and if I pull it out of the radical, it becomes a 75 like that. And then in the radical, we have 1 plus 1/8, right?
Mm-hmm.
Yep. And then we have plus 100 minus 75 root 2 on 4. And remember, if we wanted, this root 2 on 4 is because we radicalized it. If we left it in its unradicalized form, it would just be 75 over 2 root 2. And I'm actually going to do that right now because you'll see why that's more beneficial in just a second. So if we simplify what's in the radical, what do we get? We're going to get 8 out of 8 plus 1 out of 8, which is 9 out of 8. If you take the square root of 9 out of 8, you have 3, so 75 times 3 over square root of 8. And square root of 8, as we said, happens to be 2 root 2. So now we have 75 times 3 root 2 minus 75 times 1 over 2 root 2, and then the plus 100. And then obviously, as you can see, once we simplify this, this is a 3 over 2 root 2 minus 1 over 2 root 2, which is just 2 over 2 root 2, which is just 75 over root 2, plus 100, of course. And then knowing that if you have 1 over root 2, if you rationalize that, that's root 2 over 2, you can write this as 75 root 2 on 2 plus 100. And there you go. Now you've shown that the total length of the pipeline is 75 over 2, root 2 plus 100. Good? Okay, great. All right. So I think that's enough for part 1. That's a pretty good example of like word problem that's good, like I guess differential calculus, or like at least the derivative aspect of it. I don't think we're going to work out any of it. We'll do some of the harder integration problems now. So let's look at these questions now. I didn't check the answer key, but I'm pretty sure we're right, because obviously we got to the right answer, so it must have been right, unless we did mathematical error somewhere, which is probably unlikely. So now let's go to the next few set of exam questions. Exam style questions. Okay. Let's do this problem. This seems like a pretty hefty problem. Would you guys agree? I don't want to do any sketching problems here. I feel like sketching would take up too much space on, and it's difficult to do on the computer. So let's just not do sketching. Let's just do number 13 here and see what that looks like. Because it looks like a good word problem in my opinion. Okay. All right. Zachary or Maham, do any of you guys want to try this one? If not, it's okay.
I can try
Okay.
it.
All right.
Okay, this is what's it called? Exponential growth and decay. Here, where's my drawing thingy?
Okay, so let's read it. Can you read it out first? Because I don't think I haven't read it yet.
Pesticides control the population of insects in a specific area around a river. The rate of decrease of the number of insects is proportional to the number of insects at any time t.
Okay, so pause right there. So how would we represent that mathematically?
P is equal to.
Okay.
Oh yeah. Oh okay. Okay. Oh okay. Then.
Right, because right, we see that it's rate of change of the number of insects. So you can write dp dt
is equal to kt.
Yep, kt. Exactly.
Okay.
Number of insects. Sorry, kp, not kt. Because if it were kt, then it wouldn't have been an exponential growth, right?
Mm-hmm.
Yeah.
Okay.
It's proportional to the number. Okay.
Now you now you can integrate it or solve it.
Okay, you wanted to do this first before. Okay. Yeah. We can do that.
Once it's in the PO times e to the kt, that's normally when I start working.
Okay. All right. Well, let's just so we can have this written down somewhere in mathematical form, let's just write down the initial number. So p naught, so p at time 0 is 500,000.
Mm-hmm.
And then after 5 years, so p at t equals 5, p of 5, if p is a function, we say p of 5 is equal to 400,000, right?
Mm-hmm.
Okay. All right. So we know that dp dt equals kp. All right. Now, do you want to work out the integration?
I feel like you can do it because
Okay,
I feel like I'm gonna mess up somewhere.
Sure. So dp over p equals k dt, right? Separation of variables. Now integrate both sides. Now we have integral of dp over p. Well, that is just ln absolute value p. We'll put the plus c on the other side, and this is just kt plus c. Agree?
Mm-hmm.
Okay. Now to isolate p, all we got to do is say p equals e to this side. So it's e to the kt plus c, but I'll just write it out so you can see it clearly. But what you can realize is that e to the kt, that's something, and then e to the c, this is because it's an exponent and you're adding things in the exponent, this is the same as e to the c times e to the kt, right? Mm-hmm. But really e to the c is just another constant. So we can just write it as c e to the kt. So this is c e to the kt. Okay, so that's population after t years. Now we have to figure out what k is. How can we figure out what k is?
So First thing, if you know that your initial population is 500,000, basically whenever the time is 0, E is 1, so that means
Exactly.
it has to be 500. Your C value has to be 500,000. And
Perfect.
then you're doing E to the KT, and that is and it decreases to 400,000 after 5 years. So your time is gonna be, so I normally do like E to the K times 5, or E to the 5K is equal to oh yeah, like yeah. And then I divide both sides by 500,000, which will give you
Yeah.
4/5.
Yep.
Um, and then you take the fifth root to give you the value of
No,
E to,
no, natural log, right?
or oh yeah, I use regular log sometimes, but
Oh, okay. So if you use
yeah,
regular log, that would
I
actually work
change the
as
base
well.
in my calculator and
Okay, so that's actually a good point. This is a good exercise. If you don't have natural log, you can just do regular log base 10 of 4/5 equals log base 10 of this, but then if you take the log of something to the something, you can pull that power down, right?
mhm.
So now that's 5k log e, and then you can divide both sides by 5 log e to find k. But I'm going to do it the other way just because it's a little bit easier to take the natural log. So if you take the natural log of both sides, you're going to get 5k equals the natural log of 4/5. And then if you know that k equals natural log of 4/5 times 1/5. And then if you find that, I don't know what that's going to be, but that's your k value, okay? So now it asks, find the time it takes for the population to decrease to half its initial size. So we're not even concerned what C is. What we need is we need E to the KT to equal 1/2. Does that make sense?
Yeah.
Right? We just need E to the KT to equal 1/2 because that means that our initial population would have decreased by 1/2. So now what we can do, we know what K is. We can actually just take what I would actually do is I would leave it in this form first because otherwise it might complicate things. So we would actually take the ln of both sides and say KT equals ln², right? And now I would isolate T. T equals ln1/2, so ln 0.5, because that's easier to put in your calculator, divided by K. Now I can plug in K. So K happens to be ln of 4/5, which is 0.8, times 1/5, which is 0.2. And now if you plug that into your calculator, which we will do right now, give me just 1 second to put that in. ln of 0.5 divided by ln of 0.8 times 0.2, and we get 15.5 years. So after 15.5 years, this should fall to half its population. Hopefully that makes sense.
Mhm.
Okay, cool. Let me just check our answer for that one. Number 13 is 15.5. Number 13, right? Why is that not in the answer? Number 13. You guys see number 13 in here? I see 22, 20, 19, 18, 17, 16. This 13 isn't the same as the 13 we were doing, right?
Mhm.
Oh no, maybe they don't have that. Maybe they don't have the answer to that one in there. Yeah, maybe they don't. Oh well. I don't see it in there. Well, forget about it. That's okay. I'm pretty confident that what we got is okay. Maybe we made a simple error somewhere, and if you're watching this later, then you can always look back and fix us. But yeah. Okay. All right. So moving on. So number 13 was 15.5 years. Okay, so now let's go back to the document. What do you want to try now? Maybe. Oh, that's really weird. The exam practice here, the exam style questions only go up to number 15. Oh, because this is chapter 8. I don't think chapter 8 answers are in here, are they? These are just chapter 7, right?
Can we do that one Maclaurin question, even if the answer's not there?
Which one? Was it on here?
Yeah, I was at the bottom of the page. It was this Maclaurin question. It was like ln 1 plus sine
Sure,
x.
sure. Is it this one? Yeah, that's great. Let's go ahead and do this. Okay. So yeah, that's good. We haven't done Maclaurin in a while. This is paper 1. Okay. Okay. So by finding the Maclaurin series up to and including the term x in x4, show that ln 1 plus sine x equals that. Okay, so something I'm not sure about this is that on the formula chart, actually, they give you selected like Maclaurin series. I don't know if you're allowed to use those. Like,
Oh, you get that formula chart on the test?
well, during the IB exam, yes. I don't think I don't think Miss Raja like gives it to you during the test.
No. I'm saying about the IB test. I didn't
Oh
know
yeah,
that.
yeah. You'll get the formula booklet during the test.
Oh, I didn't know that.
Yeah, for sure. Okay. So, but I would actually go ahead and just find the derivative and everything. I wouldn't like just plug stuff in. I feel like that's not the best way to do it. And especially because it's 8 marks, it probably means that they're expecting you to use the whole formula. So Maclaurin series, we know f of x, of course, we know is ln of 1 plus sine x, right?
Mm-hmm.
So what would f of x equal in terms of Maclaurin?
Ln of the, or would you, so I have a question about this kind of stuff. Oh, the sum of f
The nth
whatever
derivative, right?
of
At
0
0, yep.
times x to the times n over n factorial
Over n factorial
times x to the n power.
Times x to the n power. Perfect. Good. Okay. So this is the sum we're calculating. Now, obviously, we'll have x to the 0th power, then x to the. So if we calculate f of 0, this is going to be f of 0 plus f prime of 0 times x, right? Plus f double prime at 0 over 2 times x squared plus f triple prime 0 over 3 factorial times x cubed plus f fourth derivative at 0 over 4 factorial times x to the 4th. And then, of course, we have a dot, 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 right? So now we actually have to find these derivatives. Otherwise, we can't do this. So what is f of 0, first of all? We plug in 0, sine of 0, 0. 0 plus 1 is 1. Natural log of 0, or natural log of 1 is?
0.
0. So the first term is 0. I still like to write it out to show them that I'm actually calculating that. I don't want them to think I'm not calculating. So then f prime of 0. So let's find f prime of x. What would f prime of x be?
What's the original function?
It's right here. ln of 1 plus sine x.
Sine x. So the derivative of ln of u is 1 over u, and then the derivative of sine x is cosine x. So it's cosine x.
So if we find f prime of 0, what do we get? Cos of 0 is 1. Sine of 0 is 0. 0 plus 1 is 1. 1 divided by 1 is 1. So f prime of 0 happens to be 1. So once again, I'll just write in a 1x just to show them that I calculated that. Even though I don't know how much they're expecting, but I would just write that out. Okay. You might even want to actually write out explicitly f prime of 0 equals 1. You might want to do that, but it depends because I don't know how strict they are with the mark scheme. Now, f double prime of 0, we would probably want to use quotient rule here for this. Mm-hmm. So we would use the derivative of the top is minus sine x. So low d high, so 1 plus sine x here. Low d high minus high, d low. So the derivatives of the bottom is also cos x. So we have cos squared x here over low. So we have 1 plus sine x in the bottom squared. We plug in a 0, sine of 0 is 0, so that term goes away. Cos of 0 is 1, 1 squared is 1. We have a negative 1 in the numerator, and then we have a 1 in the denominator. So this would be a minus, okay? This would be minus 1 over 3 factorial times x cubed, okay? Oh wait, sorry, x squared, and that should be a 2 factorial. I skipped a step. X squared, okay. Okay, now for the next one, I think it'll just be a plus again, but obviously we have to confirm. So now let's calculate the third derivative. So the third derivative is going to be what? We might have to simplify this out. Do you agree?
What?
We might have to simplify the second derivative out in order to calculate the third
yeah.
derivative, right? So the second derivative was what? And that should actually be an x, not a 0. F second derivative at x. We simplify whatever is up here. We would get minus sine x minus sine squared x. But here's the thing, we have minus sine squared x minus cos squared x, which is just negative 1, right, by the Pythagorean identity. So that simplifies the numerator. And then, of course, in the denominator, we still have 1 plus sine x squared. I don't think I want to distribute that out. That might make it really complicated. So now we find the third derivative of f, and that happens to be, once again, low d high. The derivative of the top will be minus cos x. So we have minus cos x times 1 plus sine x squared. So low d high minus high d low. So minus high will just become plus sine x plus 1, right? Because if you have a minus and minus, that'll become a plus sine x plus 1 times the derivative of the lower function, which is 2 times 1 plus sine x. Sorry, I'm having to squish it in like this. I don't have any better option at the moment. Times cos x, because that's the derivative of the inner function. And all of that over 1 plus sine x to the 4th power. So now, if you were to plug in 0, obviously this whole term here would become 0 because you have a actually, would it? I don't think it would turn 0 actually. Let's see. So you would have 1 plus 0 squared is just 1. Cos of 0 is 1. So we have a negative 1, then a plus. Sine of 0 is 0 plus 1 is 1. Sine of 0 is 0 plus 1 is 1. 1 times 1 is 1 times 2 is 2. We have a 2 here. And then once again, we have 1 to the 4th power. So we have a negative 1 plus 2 over 1, which is just 1. So once again, we have a positive. So we have plus 1 over 3 factorial x cubed. Noticing the pattern, we can continue and say that the next one is minus 1 over 4 factorial x to the 4th. On the exam, you cannot do this. On the exam, you would have to work out the 4th derivative and show that. For the sake of time and for the sake of space, I'm not going to calculate the 4th derivative here. You should definitely try to do that on your own though. So that would be the answer for the Maclaurin series for the first 4 terms. And obviously you would want to simplify this so it looks nicer now. Now you can write it like this. Oh, that should be a square. You can still write 3 factorial. You don't need to write out the actual values of the factorials. X to the 4th plus ... Okay, so that's part A. Now part B, hence, find the Maclaurin series up to and including the term x to the 4th. Okay, so I'm going to actually get rid of everything but the last part that we calculated because that's really all we need. So we know, oh, that was not my intention. We still need stuff here. Okay, so we know that ln of 1 plus sine x equals that, right? So how can we get ln of 1 minus sine x? Do you guys have any idea how we might do that? Because we have this to our disposal, but How can we get ln of 1 minus sine x?
You can just do like a 1 or yeah, 1 minus the element the not the Maclaurin series of sine x.
Oh, I
So
wouldn't do that. I wouldn't do that.
okay.
What this asking, if you see the word hence, that means they want you to use the answer from the previous problem. Don't, like, you shouldn't have to do like extra work to do it, figure out the, okay? So hence means, you know, like therefore or hence. So using the answer from the previous problem. So what they're actually wanting you to do is push this into this form, this ln of 1 plus sine x form. What you have to recognize is that sine is an odd function. So if I have minus sine x, that's the same as saying 1 plus sine of negative x.
Okay.
What this allows me to do is now I've pushed it into this form, ln of 1 plus sine x, and I can just actually plug in negative x everywhere I see an x. So now this is just equal to negative x minus 1/2 x squared, because negative x squared is just x squared. Now we have a minus 1 over 3 factorial x cubed. And then once again, we have a minus 1 over 4 factorial x to the 4th plus dot, dot, dot. You see that?
Mm-hmm.
Okay. Now, what about ln of cos x? How would you do ln of cos x?
Ln of
This is a little trickier, actually.
well, it's ln of cos x is all of the like the yeah, I don't know actually because it's like it's like how ln of sine is all the odds, ln of x is all the evens. So I don't know how you would do that without doing it again.
There is a way, because I remember there was a question on one of the IB problems that we did earlier that actually that was very similar to this problem. Might have actually it might have even been this problem, but let's see. ln of cos x, we need to find a way to, okay, do we have any identities that we know?
That's
Let's
what
see.
I was
It's gonna use identities, very likely. Okay, so we do know that
the square root of 1 minus sine x is cosine x, but that wouldn't, or not 1 minus yeah.
actually, let's see. Sine x I'm looking at these formulas right here. Cos of 2 theta equals, oh gosh. Okay. I really don't, I really can't think of this right now. Let's try and use this identity. Maybe it might work, it might not, I don't know. We know that sine of 2x equals 2 sine x cos x. Does that help in any way? If we isolate it, we'll get 2 sine x here. I don't think that helps, does it? That doesn't help. Okay, well, here's another approach. Maybe this might work. Sine x, cos x is just sine x shifted over pi over 2, right? So I'm thinking, could we write this as ln of sine of x minus pi over 2? Would that work? Is that true though? Is cos of x, or if I have here, let me graph that. I know we don't have access to this, but for the sake of understanding it, cos of x, and then we have sine of pi over 2 minus x. Yes, that does set them equal to each other. Okay, so now what I would do is use, I guess, this idea here. Okay, we still need to push it to this form, right? So what I would do, if I can say this is ln of 1 plus sine x minus pi over 2 minus 1, right? Does that work?
Minus 1.
So what I did was I just added 1 and then I subtracted 1 from here.
Oh, I see. Okay.
I don't know if this offers any benefits though.
If you plugged in, no, that wouldn't work though. If you plugged in x minus pi over 2 where x is, but that doesn't make any sense.
Okay. I'll come back to this one later and see if I can figure this one out. Actually, this might even be in my notebook because I remember doing a problem like this. Okay, think about it for a second and then let me see if I can find it. All right? Oh, wow, we're really dumb. Okay, no, we're not. It's just this had a pretty cool trick. You actually just have to use the Pythagorean identity. So you know that ln of cos x is what?
This ln of the square root of 1 minus sine x.
Well, a square root of 1 minus sine squared x, right?
Yeah, that was the first thing I said, and then I
Good.
didn't.
Okay. Yeah, I just didn't realize how we could use this, but yeah. So you have square root of 1 minus sine squared x. Now you factor this into square root of 1 plus sine x times 1 minus sine x. So what and why this will help is now I can write ln of cos x as ln of 1 plus sine x times 1 minus sine x.
Oh.
And raise this whole thing to the 1/2 power. And then the nice thing about this is now it's a log, so I can bring this 1/2 down. Now this is 1/2 of ln 1 plus sine x, 1 plus sine x, plus ln of 1 minus sine x, using our log properties. So now we already have these two, so now we just have to combine them together. So if we add these terms together, the x and minus x will go away. Minus half x squared becomes what? Minus x squared, right?
Oh, okay.
This and this will cancel, and then minus 1 over 4 factorial, so that becomes minus 2 over 4 factorial. X to the 4th, and then of course dot. And then if you wanted to simplify this, this would be minus 1/2 x squared minus 1 over 4 factorial x to the 4th minus dot. Okay, that's how we do ln cos x.
Okay.
Now ln tan x. Well, this is another challenge, right? How would you do ln tan x? Well, I think one approach is to do sine x over cos x, right?
Yeah.
But that probably wouldn't work, would it? Oh wait, it's not ln tan x.
If you did ln of sine x minus ln of cosine x, that's the same thing as ln of tan x.
Well, here's the thing. It's just tan x. It's not ln, which is I just realized that. So it's tan x. So we need to represent tan. Wait, tan is the derivative of. There might be a way to do this using a derivative.
The derivative of ln of cos x is.
Yeah, the derivative of ln cos x
is it's
minus tan x, right?
It's the wait. The derivative of cosine x is sine x, right?
Yeah, no, but I'm saying derivative of ln cos x
Yeah, so ln cos x, so one over cos x, and then chain rule, so the derivative of cosine x is sine x.
minus sine x, and you get minus tan x.
Oh, it's minus,
So
yeah, yeah,
yeah, so
minus,
now you can just put a minus here. You can write that as d minus d dx of ln cos x. And guess what? We already found ln cos x, so we can now just, so once again, if you see that word hence, you're probably going to have to use things from previous parts of the problem. So that's equal to minus d dx ln cos x. D dx ln cos x is just minus the derivative of whatever's inside here. The derivative we can easily calculate as, so this would be minus x, right? This would be minus x. And then this would be minus 1 over 3 factorial x cubed. And then obviously the next term would be the x to the 5th term. So we don't need to worry about that because we only need to find up to x to the 4th. Then we have dot, dot, dot here. And then, of course, if you just put the negative sign, that'll become x plus 1 over 3 factorial x cubed plus dot, dot, dot. Wow, that was a tricky question, but we got it. Okay, good. So now, finally, we have to calculate the limit as x approaches 0 of tan of x squared over ln cos x. You can calculate this using L'Hopital's rule, but given that it's a Maclaurin series, they probably want you to do it using Maclaurin. So let's see how you would do this using Maclaurin series. So you have limit as x approaches 0. On the exam, you'll have to write it out fully limit, but right now I'm just writing I'm just writing the limit. I won't even write limit right now because I don't have space for that. So tan of x squared is actually this function right here, but you plug in x squared. So you would have x squared plus 1 over 3 factorial x to the 6 plus dot, dot, dot. And on the bottom, you'll have ln of cos x. ln of cos x we figured out was minus 1/2 x squared minus 1 over 4 factorial x to the 4 plus dot, dot, dot. Now, what we can do is we can factor out x squared from the top and the bottom. If we factor out x squared from the top and the bottom, we're going to get x squared times 1 plus 1 over 3 factorial x to the 4 plus dot, dot, dot. And then in the bottom, we're going to get x squared to the times minus 1 over 2 minus 1 over 4 factorial x squared plus dot, dot, dot. And now what this allows us to do is, because we're calculating the limit as x approaches 0, all these terms will go to 0. All of these terms will go to 0. X squared and x squared cancel, and we're left with 1 over negative 1/2, and that happens to be negative 2.
Oh, okay.
So that this is yeah, you can do it using L'Hopital, but this is the better way of doing it, I would say, using Maclaurin. Much easier than L'Hopital, actually. And I actually think this was on the IB exam one year, this problem. Okay. So that's a good review of Maclaurin series, and that was a pretty actually complicated problem. It's 7:06, so I realize we've gone past an hour, so if you need to leave, I completely understand. Let's just do one more problem. Is there any particular problem you want to do?
No, just pick the hardest one that you can find.
Okay. Well, what if I don't want to be the particle? Be the particle. No, I don't want to be the particle. Okay. let's just do this other one, number 14, because it's towards the end, so I'm assuming it's probably going to be a little bit more difficult.
I saw on the IB review that they didn't do linear. They just did homogeneous. Like on the 157-page review, I didn't see linear anywhere.
You didn't see first order linear?
Yeah, I didn't see first order. For some,
well, I know it's part of the curriculum, so maybe they just, I don't know.
Because I didn't see it anywhere. Maybe yeah, okay.
Come to think of it, do you want to practice a linear, do you want to practice one of the differential equations?
I honestly feel like I don't know if Zachary needs practice with that, but like it's, for me, it's kind of just like, I kind of just memorized how to do it, so.
Okay. Yeah. So then let's just stick with number 14. I think we'll just do number 14.
Okay.
Okay. And then if we have time, we'll do the other one as well. Zachary, anything particular? I don't want to waste your time. So is there anything particular you'd like to do? Okay, that's fine. Maybe he's out for a second. Or,
Yeah, no. Yeah.
okay.
I went to get some water. So
Oh, that's good. That's all good.
I'm fine.
Okay. Oh, okay. This is actually a differential equation. How funny. So given that dy dx equals cos x times cos squared y and y equals that when x equals pi, show that the solution of the differential equation is that. So that's nice. They're telling us what it has to be. So if I have dy dx equals cos x times cos squared y, what's the best way to do this?
I think just dx, like separation of variables.
Yeah, separation of variables. Perfect. So one thing I will say, I'm not going to actually write cos squared y because to save time, you can actually just write sec squared y here, right? Because once you divide that, that'll be sec squared y, right?
Mm-hmm.
And on the other side, you'll have cos x dx. Integral on both sides, integrate both sides, and you'll get tan y on one side, and you'll get sine x on the other side, right? Sine x plus c. Now we use our initial condition. X equals pi. Sine of pi happens to be what?
0.
Pi over 4. So, and then plus c. Okay, so that means c equals, so if sine of pi is 0, then tan c equals tan of pi over 4, right?
Mm-hmm.
And tan of pi over 4 is just 1, because sine of pi over 4 of cos of pi over 4 is 1. So c equals 1. So that means, using this information, we know that tan of y equals sine of x plus 1. And we know that y then has to equal the arctan of 1 plus sine x. And there we go. We've shown that that's the solution of the differential equation. Okay?
I know how to do homework. I don't really want to go over that just because I kind of have to leave soon. But like,
Sure.
do you explain like what? Like, I know when you would use homogeneous, right? When you can write it as like y over x, or like if they're all going to the same power, whichever one you would rather.
Yeah.
Do. Yeah, but and like when would you like use homogeneous? Like when would it be? Like, is there times where you just can't use separation of variables?
Homogeneous you have to use because you can do separate. If you could do separation of variables, always do separation of variables first. That's the easiest thing to do.
If you can't do separation of variables and you can't write it in the form y over x, like all the,
then you go to linear, and then other than that, you won't see ones where you can't do that. There's actually second order differential equations. You could do, and there's different methods of solving them, but we don't. That's not in the syllabus.
Okay.
Yeah.
Okay. Thank you.
Okay, let's just do part B, and then I'll end it for today, just because I realize we're taking a bit of time. But I hope this was productive. I hope this wasn't just a big waste of time. Okay. Determine the constant k for which the limit exists, and then evaluate the limit. Okay, so we want the limit as x approaches pi over 2 of arctan of 1 plus sine x minus k divided by x minus pi over 2 squared. So my understanding for this is you're probably gonna have to use L'Hopital's rule, right?
Mm-hmm.
It doesn't seem like this is something that's gonna come easily just by, So if you do L'Hopital's rule, I'm gonna drop the limit for now, just for the sake of time. But if you use L'Hopital's rule, you should get, on the bottom, you would get 2 times x minus pi over 2. And then on the top, you would get, this portion is y. So if we find this portion will actually just be cos x cos squared y, right?
Mm-hmm.
Okay, because that is y, okay. And then minus k, well, if you take the derivative of that, k just becomes 0. So how would you do this? Determine the value of the constant k for which the limit exists. Well, when does the limit exist? What does it mean for that limit to exist? Limit as x approaches pi over 2. Well, x approaches pi over 2. Sine of pi over 2 is 1. 1 plus 1 is 2. Can we ever have arctan of 2? Oh, that means I'm okay. Obviously, that doesn't work. I don't think I'm understanding this fully. I think this was one of the IB problems as well. I don't think I fully understood when I did it. Obviously, because otherwise I would have been able to solve the problem right now. Let me see if I can find it. If not, then think, because honestly, I don't know. This is really weird. This is rather difficult. Can you think of it right now? Like, what would make it?
I'm trying. I'm splitting it up. Like that's gonna help, but it's not.
That's a good approach.
Yeah, cause no, but then k is a constant, and it would go to 0 if you split it up using Lopi.
Yeah, that's what I tried doing with L'Hopital. I don't understand what that means. What does it mean for the limit to exist? I can't find it. I'm sure it's in here, but I can't find it at the moment. Okay, well, if the limit exists,
Maybe
then, sorry?
they've written a function so that it's in the form like f of x over g of x, but you need to find the original function or no.
Zachary, do you have any ideas?
Not really. I'm kind of lost too. I'm stuck.
Arctan 1.
Oh, I know. Sorry, this just ran across my head. Okay. So here's the thing. We can use L'Hopital. I'm sorry. This is L'Hopital, right? But when can we use L'Hopital?
When it's in indeterminate?
Indeterminate form. So if it's an indeterminate form, k can't just be any willy-nilly number. The numerator has to equal 0. So we know that in order to, and you would have to write this out probably, but in order to use L'Hopital's rule, we know that arctan of 1 minus sine 1 plus sine x minus k has to equal 0. If it doesn't equal 0, then we can't use L'Hopital's rule. So now you use L'Hopital, or now you solve for k using this. So that means k equals arctan of 1 plus sine x, right? Because otherwise you can't use L'Hopital's rule. But it's a constant, right?
Mm-hmm.
So I guess you would plug in pi over 2. Yeah, you have to plug in pi over 2. Then you would have to plug in arctan of sine of pi over 2 is 1. 1 plus 1 is 2. So it's arctan of 2. That's your constant.
Oh.
Because then that lets it equal 0 over 0, and now you can do L'Hopital.
After.
Okay.
They're like two independent things. Not independent, but like, you don't need the first one to do the other. But, okay.
So now if we were to evaluate the limit, well, now let's try plugging in pi over 2. Cos of pi over 2 is 0, right? So in the numerator, we will get 0. And then in the bottom, we still get 0. So I think we have to use L'Hopital again. Right?
Do you still get 0? What is it? 2x minus pi over 2. So if you pi minus pi over 2 is.
But it's pi over 2, right? We want x to equal pi over 2. So if I plug in cos of pi over 2 is 0. So the numerator is 0, and then pi over 2 minus pi over 2 is 0. So we get 0 over 0 again, right?
Sorry, I'm a little slower at this.
Okay, that's okay.
So okay, yeah, 2x minus pi over 2. So you're plugging in pi over 2 again. Okay, yeah.
Yeah, okay. So now I guess we would have to do L'Hopital again. And I'm going to say the denominator just equals 2x minus pi because that makes it easier to differentiate the next time. So the next time we differentiate it, in the bottom we'll have 2. And in the top, it's product rule, right? Derivative of the first function, which is minus sine x, times cos squared y, plus the derivative of the second function times the first function. So this will be, plus 2 cos y times the derivative of cos y, which is minus sine y, times dy dx, right? Because we have to differentiate y with respect to x. And then we have to multiply the cos x again, so this one, cos x. So we have to multiply times cos x. So now, as x approaches pi over 2, what happens? Sine of pi over 2 is 0, so this goes away. We don't need to worry about that. Let's see. So now we have 2 cos y times minus sine y times dy dx times cos x. Okay, well, cos of pi over 2, wait, I did this wrong, didn't I? I did this wrong, I'm sorry. Sine of pi over 2 is 1. We should probably just manually write this out, shouldn't we? Yeah. Okay, we still have a 2 in the denominator. Sine of pi over 2 is 1, so that's a negative 1. Cos squared of y. So y was what? Y we solved here, arctan of 1 plus sine x, right? So if we plug into pi over 2 here, pi over 2 plus, sine of pi over 2 is 1 plus minus 2. We have arctan of 2, so we have cos squared of arctan of 2. Are we doing something wrong here?
I honestly don't know.
Okay. Well, here's the thing. I think overall we understood this problem. I think part of it is the space as well. I mean, it's definitely cramped up. But I would definitely try doing this problem and finding the limit. Because we figured out that this is what would happen. We figured out what k would have to be. Actually, I really do think we did this problem. So I'll look through it later and I'll put it in the description if I find the solution. Okay? For the limit that we couldn't do. Okay. So that's pretty much it. We've done exponential growth. We've done differential equations. We haven't done homogeneous and linear, but you could try that on your own time. Okay, we didn't do everything, but I think we got a decent review in, right?
Mm-hmm.
Okay. All right. Thanks, guys.
Thank you. Okay.
All right. Bye.